Welcome to part 2 of the PSA Gateway and Node Data Logging System. In part 1, the Gateway and Node Data Logging System was introduced. We covered data flow from the sensors to the cloud, the hardware, and benefits of the wireless system. Today we'll cover what's inside the shipping box and how to check the hardware. We'll also touch on Gateway and Node synchronization and review the collected data. As a member of the PSA data collection team, you'll receive one or more Gateway and Node data logging systems. What should be in the box? The box contains one gateway, 2 nodes, 4 antennas, and several sensors. These are what's needed per farm site. If you have multiple farm sites, you will receive several sets of the system. If something is missing, contact whoever sent you the box and get what you need. You need to check the hardware to be sure it's in good shape. This includes checking cables for any nicks and opening the enclosures to check for key components. Inside the gateway, the one with 2 antenna jacks, check for the SIM card, micro SD card, battery, and note the barcode and serial number inside the enclosure door. You'll need it to verify it matches the serial number stored in the gateway's memory. Inside the node, check for the battery, sensor connector, and the barcode and serial number inside the enclosure door. You'll need to verify this one too. This portion of the video shows how to use the Arduino IDE to interact with the gateway and nodes. This information may not be needed, but is provided for just-in-case situations. You'll need a PC, a micro USB cable, and the Arduino IDE. Download it from the Arduino.cc software tab. Once you've installed the Arduino IDE, open it and you'll see a window like this one. Connect a node or gateway to the PC with the USB cable. Click the Tools tab and hover your cursor over the menu Port option. Select the COM port your device is connected to. If you're not sure, unplug the device and check to see which port is no longer listed. The serial monitor is the window used to communicate to the device. Open the serial monitor by clicking on the magnifying glass in the upper right-hand corner of the Arduino window. You'll need to change some settings the first time. At the bottom of the window, select No Line Ending and the correct baud setting. Before covering the Gateway and Node user menus, let's cover key identifiers to help you understand what's in the menus. 2 fixed identifiers are the serial number and firmware version. The serial number is unique to each device, allowing tracking of its location. The firmware version number identifies the revision date and is set in the firmware. Both of these identifiers are included in data strings sent by the devices. Other identifiers include the radio and project IDs. These 2 values are set during the initial configuration and should not be changed by the user. No 2 radios within close proximity should have the same ID. Its default value is the last 2 digits of the serial number, but can be changed to a value between 0 and 99. The project ID is a global ID used to assign the incoming data to a specific database. All devices in our project should have PSA as the project ID. The gateway also has a unique device key identifier. This is used to allow the device to send data to our cloud service provider, Hologram. This value should not be changed by the user. Now let's look at the gateway user menu. When you open the serial monitor with the gateway connected and on, data will stream into the serial monitor window. The header at the top of the data lists the key identifiers and information about the network setup. You'll see the firmware version, the gateway serial number and radio ID, the number of nodes, and their radio IDs. You'll have 2 or 4 versus 1 as shown in the figure. Verify your radio IDs match what's listed in the header. You'll also see the file name for data stored on the SD card and 2 timing intervals, one measured interval for how often the gateway receives data from the nodes and an upload interval for how often data is sent to the cloud. The last items are time and battery voltage. The timestamp will be incorrect on startup, and that's okay. The batteries you received may not be fully charged. If you connect your PC to the device and the battery voltage is less than 3.4 volts, you'll see a warning indicating you need to charge the battery. If the battery voltage drops below this limit in the field, the unit will enter sleep mode to conserve energy until the battery is charged. The solar panel charges the battery when exposed to sunlight. You can also connect an external power source that provides between 8 and 30 volts DC to charge the battery. The charging LED indicates the battery is charging. Below this section of information is a list of user input options. To select an option, type the character corresponding to the action you want in the input bar at the top and press Enter or Send. The gateway is pre-configured, so you shouldn't need to access these options. It's a good practice to check your network connection by selecting option C to connect to the NIST time server to be sure the gateway is working correctly. Now let's connect to a node. In the serial monitor window, you will see the hardware information, a message about the status of the log space setup, and an option to enter S to skip the sensor scan. If you choose to skip the scan now, the node will scan for sensors when you exit the menu. The sensor scan finds active sensors, then lists their IDs. Verify that the sensors found match what is connected to the node. We use 4 types of sensors: the Acclima TDR310H soil water sensor, 3 for the bare treatment, and 4 for the cover crop treatment. The cover crop node will also have a relative humidity and ambient temperature sensor, and a temperature sensor used with the decomposition bags. Information within sensor IDs include the address, which indicates treatment and depth, product ID indicates sensor type, and the specific sensor serial number. Below the sensor scan, there's information similar to what we saw earlier with the gateway: the firmware version, node and project identifiers, gateway radio ID, measurement interval, and current time and battery voltage. Again, remember to verify the radio IDs match those on the gateway. Below the header is a list of menu options. The node is pre-configured, so you should not need most of these options. You can use option T to take test measurements from the sensors. Once the menu routine times out, the gateway and nodes will enter the initial synchronization routine. If you leave the serial monitor open, you can watch the synchronization between the gateway and nodes as it happens. The system will execute this synchronization every time the gateway and nodes are powered on. We'll present a summary of this process. During synchronization, the gateway and nodes establish communication and synchronize their clocks. The gateway sends a message confirming initialization along with initial test measurements taken by the nodes to the cloud. These messages confirm the system is working properly and can be checked for on the web using Slack or the PSA app. Synchronization should take from 10 minutes to 2 hours, but is usually less than 20 minutes. What does the data look like? Data from the gateway and nodes are sent in delimited data strings like this one. The gateway sends metadata to help us monitor its performance. The gateway data string has the firmware version, project ID, and serial number, followed by the battery voltage, enclosure temperature, and the current and voltage generated by the solar panel. Last is the timestamp and coordinated universal time, or UTC. The node data string includes the same metadata: firmware version, project ID, serial number, battery voltage, enclosure temperature, and measurements of the power generated by the solar panel, and the timestamp and UTC. The sensor data starts after the metadata. First is the soil water sensor data, which includes the sensor ID, measurement center depth, volumetric water content, soil temperature, permittivity, bulk electrical conductivity, and soil pore water electrical conductivity. The measurement center depth corresponds to the midpoint of the sensing volume along the waveguides. Temperature and humidity centers output similar data strings with sensor ID, measurement center depth, and temperature measurement, and a relative humidity for the relative humidity sensor. The received signal strength indicator is added to the end of each data string by the gateway. This RSSI helps us know if something is interfering with the data transmission, so we go out and inspect the antennas and reconsider the placement. This video covered a lot of information. Let's end by looking at the bigger picture about why we're doing all of this. The gateway and node wireless data logging system allows us to remotely monitor soil water content in real time and pass that data on to the grower. We can also monitor system performance to ensure operation and address issues in a timely manner. Databases and interfaces are being developed to allow quick access to the data. Other sensing systems are being developed and integrated with our data platform to further expand the type of data we collect. The data are being used to develop and validate models that explain and predict cover crop effects on cash crop performance across climates and soil types. These models will be packaged into decision support tools growers can use to make informed decisions about cover crop management, and that will help expand cover crop use across the country. As this collaboration expands and evolves, so will its reach and innovation. In a changing world, research collaborations such as this lead the way to a more sustainable future. If you'd like more information on soil water sensing in PSA, check out these videos on the PSA YouTube channel. Thanks for watching.